We go into new chapter, chapter 7. So I can see for this module you have 4 LO. LO1, LO2 will be in your test 1. So LO3, LO4 will be in your test 2. Then your final exam will cover all. LO4, you have 2 questions. There will be 2 questions come out from for the LO4. Choose either one. Choose either one. Now today we learn how to make the metal stronger. We learn about strengthening mechanism. We will learn what is solid solution strengthening. We will learn annealing, then how to do precipitation, and then recrystallization. First, solid solution strengthening. So by the word of solid solution, it means you deal with um, metals that is molten, right? And then you add in impurity atoms, right? You add in impurity atoms to get the product is called alloy. The product is called alloy. And there are 2 types of solution. One is interstitial, and substitutional. Previously, you learned about defect, right? Defect, you have a hole and extra, you have a hole and also you have an extra space there, right? So substitutional means you replace atom, replace the atom, and institutional means you find the gap between the atoms, right, or molecule, and then you fit inside there. Previously, there's an example to calculate the space or the atoms that you fit inside the uh, the crystal structure. So we have 2 types. Okay. So you have seen this one in the previous chapter. So the one that replace the original atom in the green color, this one is called substitutional. And those that fit between the space of the holes is called interstitial, right? Interstitial strengthening. So these are the 2 types. Okay, so when you substitute this one, the green ball, the green atom, when you substitute, it's like you having you go to fix your car, and then you cannot find the original parts. Then you fit in the the spare part. So sometimes the the atom, if it's not the same element, the radius will be maybe 98% same, but it will not be exactly the same, right? So if the green color atom here is a little bit bigger, so it's going to squeeze the neighbor. It's going to squeeze the space around the neighbor. So when it squeezes, then it creates stress. It creates stress. Then when you push the green ball, if the green ball have a bigger radius atom radius, a bigger, it creates stress. It means it will take up some space there. So the movement will become harder. When the movement become harder, it gives you the strengthening behavior. Means if the atom is very hard to slide along the axis or the crystal structure, then it make the metal become stronger. Okay. So the concept behind for the substitutional is that when you substitute something, you create stress field. This stress field will make the movement more difficult. Then it contributes to the strengthening of the material. So you're given 3 graphs here. So these 3 graphs, you read the y-axis. So y-axis, the first graph is the tensile strength and the nickel content percentage, right? So you have been learned how to calculate the weight percentage in one of the chapter before this. And in chapter 6, you learn about how to find the tensile strength, right? The second graph is yield strength. Right? Yield means it already it already passed the elastic point. Means cannot go back already. Cannot go back to original point, original shape. Then this is also nickel content from 0 to 50, yeah? 0 to 50%. Of course, it's a big graph. This is just a crop part of the graph. The third graph here is elongation in percentage, right? Elongation versus nickel content also. So you can see from the graph, if you increase the impurity, impurity means the alien or the foreign atom that you add in. So impurity, you add in, so you can see the tensile strength will increase. Tensile strength will increase. Right? Tensile strength increase, what does it mean? If we on the tensile graph, it means you shift the graph higher and higher. So if you plot your tensile graph, all right, stress versus strain. Let's say this is the original form, okay? You know that this is your yield strength, right? Okay. Or at the end point of the linear line, huh? So if you add nickel, your graph will go a bit higher. Like that. So this is yield number 1. If you add maybe 10%, so you'll shift up a little bit. Okay. So this is how it means. And again, on the graph, you have two axes. One is on the left is megapascal, on the right is the imperial unit. In your assessment, look carefully, especially your test, final exam. Uh, look carefully on the graph. The second graph on the middle, the yield strength, tensile strength, yield strength. So this one also increase. The third graph, elongation percentage drop. Why the third graph, the green color curve drop? Because just now, what is strengthening mechanism by substitutional? You substitute great stress is not able to move freely. So the elongation cannot happen. There's a resistance to elongate. Okay, there's a resistance to elongate, so you drop. So just now you mentioned about stress field. Now you look at this diagram. So this diagram you put in a smaller atom, what is called interstitial strengthening mechanism. So you put inside a smaller atom there. So when you smaller atom and you create force, it's like doing packing. So doing packing, the surrounding will push towards the empty space here. So this one will also generate lattice strain. You know what is the word strain itself is a deformation. Right? Strain is definition of strain. This one is change of length divided by length, original length, or it can also means diameter and divided by original diameter. There's one example. There are a few examples. One, you calculate the length. One is on the diameter. Okay, so there are few definitions. Look carefully the question. All right. So here, if you have impurity, you're going to have lattice strain on the surrounding host atom. Okay. So this on the left is the one that is smaller host. On the middle one is the one that you saw just now. If the atom is a bit bigger, then you have compressive strength. On the left, you have tensile strength. What I mean by tensile, you are pulling the thing, right? So this one, the atom is pulling from side. So you imagine here, you pull to the center. So it's a tensile. But you have a bigger atom, you squeeze, means you compress the surrounding. Okay, so you have two. One is tensile strength, one is compressive strength. It depends on the size of the atom. Okay. As you read, huh? Okay, as you read. Now recall there is a symbol inverted T that you learned in the previous chapter when you learn about defect, right? So this one, there's an inverted T here. It means something missing from this point onwards. So this symbol also called edge dislocation. So when there's a edge dislocation, there is a smaller substitutional impurity atom. You can put inside here, right? You can put inside here, and you know that just now have two diagram, huh? Small atom, it will create tensile strain. Big atom become compressive strain. So here, if there's a space, there's an edge dislocation, means there's a space there. So when you do alloying, you put in atoms. There are two types of alloying. One is substitutional, one is interstitial. So in this case, you see the atom is smaller, so it's under interstitial strengthening mechanism. So here, when you put inside here, the surrounding will go inside, right? Go inside. So the packing will do, and then you will create a tensile strain. Okay, you experience tensile strain on the slip plane. There's another one. Same edge dislocation. So here you put in the bigger atom. So you will create compressive strain to the surrounding. Huh? So the importance of these two diagrams, it talk about resistance. The resistance to slip. Slip means you allow the atom to move. So the more easier the atom to move means more easier to deform. For metals, for metals. So resistance to slip is greater when your alloying atom or impurity atoms are present, because the lattice strain must increase if the dislocation is torn away from them. So there are two factors how you do solid solution strengthening. You look at, I'll give you two. There are two. So you imagine you have now you have a hole there. Then how you fit inside the hole means you want to do strengthening. So first you look at the size factor or relative size factor. So by the size, it will create the type of strain inside the lattice side. So here it will create the lattice distortion that contribute to the resistance of movement. Resistance of movement, the first one. The second one is short range order. Short range order, it means the repetition of pattern, right? Repetition of pattern. So this one is more on the bonding structure. Later, when you learn about polymer, or later in the last chapter, when you learn about polymer, then there's a long range and a short range. Even in the previous introduction chapter, you have been told what is long range, what is short range. All right. So there are two types that we need to consider when you do strengthening. Either size. Most of the time we look at the size, and then if it's in the repeated pattern, or like for example polymer, then you need to look at whether it have a short range order or not. Right? For number two, is rarely happen in metals material. Unless there are some when you mix the pure element, then something wrong with the process, or they already have some impurity inside the pure metal powder or something, right? So the next one is more on technical term, strain hardening. What is strain hardening? This is the definition for strain hardening. Strain hardening is a phenomena where a ductile metal become harder and stronger as it's plastically deformed. So strain hardening, you need to go through one keyword here is plastic deformation, right? So it must go through a process called plastic deformation, and it happened to ductile material, right? Ductile material. So you have uh, two types of deformation, right? You still remember the two types of deformation. One is elastic deformation, and one is a permanent deformation or plastic deformation, right? So this one happened to plastic deformation, and then ductile means it is easier to pull easier to pull like a extreme case is like a bubble gum, but metal won't be bubble gum, but it's behave like bubble gum. Opposite meaning of ductile is brittle. It's like a glass. So this one happened in the ductile material. Ductile material, for example, aluminium. Previously, you learned about the process of producing metals, right? Pulling, hammering, and all this, right? So in this case, when you do about strengthening for solid solution, when it comes to strain hardening, there is two type. They have two type of strain hardening. One is called cold working and hot working and cold working. This one you also learn in one of the process. So there's a formula. I think this one you learned before. Percentage of cold working, right? The percentage of cold working, you take original times 100%. Or in calculation, because the area normally is the round one, so you'll get pi r square or pi d square divided by 4. Pi and 4, they are constant value, or pi is a constant value. So you only deal with radius or diameter. So you still come to the strain, the diameter. Okay. Okay. So for cold working, it depends. You have original square shape and cylindrical shape. So cylindrical, you use pi r square. For square one, you need to use the side, the side to get the area. Just be careful on the side of the sample. Okay. So you have three graphs here. So three graph here on the left, on the y-axis is the yield strength again. And right-hand side also use strength, but imperial. So for our module, we only interested in unit SI. So focus on the unit SI. Not necessarily your unit SI is on the left. You need to read carefully. Sometimes it's on the right-hand side. Okay. Percentage of cowork on the x-axis. The middle one is tensile strength versus cowork. The last one on the right is ductility versus percentage of cowork. Right. So ductility, there's a percentage of elongation. So if you can see how you apply this one in your calculation or in your assessment or maybe in your lab report. So different material have different properties. Later in one tutorial question, we will use one of the graph here. So when you see this kind of, when you need to use this graph is that when the customer tell you, I want to meet a certain criteria. For example, the end result. The end result maybe I need 500 megapascal for my yield strength. The end results. So from this information, you read the graph, and then it tell you the elongation, percentage of elongation cannot more than maybe 30%. You have two, and then something else. It will give you tensile strength on a certain value. So you go from one graph to another graph. So for example, in this case, if the customer tell you that the end results, it need to have minimum, let's say 500, not 500, this one too big, maybe 300. So you go in from 300, then you draw a line. You have two value there. This one you cannot use because the customer want, let's say 300 megapascal. So you reject the third element. Then you only look at brass or copper. So brass or copper give you maybe this one 12% co-work. This one 35 lah, maybe 32%. So these two, just now there's an equation, right? Percentage of co-work equal to area original minus deformation divided by original times 100. So there's a certain limitation in the process where you cannot over this percentage. So you need to read the question carefully. So for example, the customer want the end result is the 300 megapascal. So you draw a line and then you go down and there's a percentage there. Then you move to here. It will give you like after the process, let's say you have 12 and 35%. You have two, there's a range there. Then it tell you the tensile strength of that final product. Maybe it should mean maybe 350 here. The tensile strength. The customer want 350. Just now is a yield strength. Yield strength, customer want 300. Now the customer want add in more information. He want tensile strength 350. So you go in there, draw a line. So you have a range here. What does the co-work percentage means? It means if you want to reach 300, you need to do at least 12% co-work to meet this value for brass. Same with copper. You need 35%, then you only can reach 300. Same with here. So here you do core work 10%, you will get a tensile strength, this one, 350. Of course, higher is better, right? Higher is better. Let's say you use brass, 12%. You go in here, 12%, you'll get higher than 350. So 12% is good for brass, right? And same with the core work. Later we look at one example how to use this graph. So it's just that how you extract the information for that one. So the percentage of core work will you need to apply this percentage of core work equal to area, the ratio of area times 100%. And you need to read carefully what is the customer want. This is another graph, strain versus strain. This is a tensile graph, stress versus strain. As you can see, the change of percentage of core work, the more core work you have, the higher the mechanical property is. Same material, this one is on the low carbon steel. Original one is a blue, is a green color one. Then if you do 4%, it increase a little bit. The 24%, it gets steeper and steeper. Okay. And you can see the green color here. This is called plastic region. The green color, this one is called plastic region. As you can see, if you do core work, means you do hardening, strain hardening on a brittle material, it will increase the plastic region a bit higher. You'll push the plastic region a bit higher. Another one is called strain hardening. This is stress versus strain also, right? So how do you do the strain hardening? First, initial metal with yield strength deform at point D. So how to read this one? Now, normally when you have a stress versus strain graph, how do you determine yield strength? Previously, we used 0.2% strain, right? 0.2% means 0.002 strain. Okay, you do this one, then you get the yield strength. So in this graph, let's say you do 2%, you get point D. Okay, point D. Then stress is released and reapplied with the resultant new yield strength yi, this one, right? So in this case, you load until this stress, and then you reload again, and then this it means you pull and then you let go. You pull, you let go. Here, this red line means you apply force from the origin, from the zero here. You apply force until this point. Then you let go the load, means the reading will drop to zero. Why it do not drop back to the left hand side? Because you already passed the elastic region already. Okay. Why this one do not drop back? Because it already passed the elastic region. If it's inside the elastic region, then it will fall back. You still get back the original behavior. So this one, D already start to yield already, means it do not show elastic behavior. So when you release the load, it will drop back to zero. The stress will drop back to zero. And you apply the load again, you will get this strengthening, we call strain hardening, recovery and strain hardening. By this process, the metal becomes stronger. As you can see, from here, maybe from here, it reach here, right? I think something wrong with the graph, right? It means the D may be original here, it will reach here. Okay. Okay, then we start to look at how we do the process. How we do the process. So now we look at 70% copper and 30% weight percentage. This weight percentage. If you forget already, go back to that chapter that you learn how to calculate the weight percentage. Right. 70% copper, 30% zinc. On this graph, on the left is tensile strength. This one is in imperial unit. On the right is, on the x-axis is percentage of forward. Y-axis here is elongation. So you have three different axes. At the moment, you ignore the imperial unit first. Right? So you have elongation, yield strength, and tensile strength. So on the three line here, only the lower, the dark blue color is referring to the right-hand side of the y-axis. The other two is referring to the left-hand side, left-hand side, because the axis tell you the left-hand side axis is tensile strength and yield strength. So you're referring this graph, these two lines to the left-hand side. Don't read the wrong one. Then on the right-hand side, this one is okay. Left-hand side is the unalloyed or hydrogen-free copper. Left-hand side is the one that we want to look into. Left-hand side is a pure, can say pure copper. Left-hand side is alloying. You already alloy the metals. So you can see what happened to the line. The elongation from 0 to 60, the elongation line can say not much different. Look at 20%. 20% give you 25%, 22, 2%. Yeah, so the elongation actually increased if you read the graph carefully. How you know is a bit increased? You look at the elongation line. On the left-hand side is a pure material. So let's say I pull in 20% cold work. I get my elongation about here. So it's about maybe 18%. So you go here, you also do 20% cold work. You go up, then you move to the right here, will be about 25%, maybe. Right? So you see the if you increase from original copper on the left to the right hand side, when you add in zinc, 30% zinc, the elongation increase a little bit, because you already changed the behavior. And then or in other words, you want to get 80% elongation. Let's say you want to fix the elongation. So 80% is here, right? Then about here, right? 80%. So you move back to this line. You move back to this line, you move, is about 24% cold work. 24% cold work to get the same elongation. Let's say you want to stay elongation at 80%. The cold work you need to do on the pure copper is 20%. But if you want to stay 80% elongation on alloy material, it is 30% copper plus 30% zinc. You need to do more work to get the same elongation. So in this case, on the right hand side, the green color graph, you need to get roughly like 24-25% cold work. Then only you can get the same elongation. Okay, this is how you use the graph. Okay, I think we stop here. We have a short break. We have a 10 minutes break. We continue 9 o'clock.